Hello, everyone. Welcome back to our YouTube channel, Becoming a ROS Developer. Today, we have with us one of our students, Mohammed, who has completed the course ROS 2 Navigation in 5 days. And at the end of this this course, you can complete a project and implement it on a real robot. So that's what we're going to see today. We're going to see Mohammed present this navigation nav2 project basically on a real robot. So, hello, Mohammed. How are you?
I'm good. How are you? Good morning, everyone.
I'm good. Good morning to you as well. So, yes, whenever you are ready, you can start sharing your screen and tell us how you've achieved your project.
Perfect. So, as told before, my name is Mohammed Ghasef Paracha. I graduated from Texas A&M as an electric engineer, class of 2022. And now, currently, I'm doing masters in electric engineering at University of Houston, class of 2025. So let's do the demo first. You can see my screen, right?
Yes, I can see the robots.
All right.
Sorry.
So, as you can see here, I will first localize the robot. Here I have ROS open. Oh, I think it reset, right?
Yes, the cameras will come back in just a second.
No problem. So I'll continue with the presentation. So the robot is Turtlebot 3. It is running in Barcelona, Spain, and it has robust embedded systems, and it has 360-degree distance sensors. So first of all, the project involves building the map. Maps and navigation, they serve for localization and trajectory planning, and it's based on occupancy grid maps in ROS 2. The essential components are LiDAR, odometry, and SLAM, which is simultaneous localization and mapping. Inside cartographer, which facilitate map creation. The cartographer is a real-time SLAM. It's a system developed by Google, and it provides robust mapping capabilities. And we have a navigation lifecycle manager. It's basically like it manages all the nodes with the streamlining, and it is like an efficient way for navigation systems. So the takeaways basically from the first part were that the maps are foundational for robot navigation tasks. Cartographer simplifies map creation with real-time SLAM capabilities, and understanding that how navigation lifecycle manager enhances node management efficiency. So let me just check. Yeah, so the robot is back on.
Nice.
So let's do demo first. All right, so here I have the terminal. So first of all, I'll just show it again. So I've already built all the packages. So I'll launch the localization. And I guess I'll show the ROS from start as well. So I have pre-made ROS file, which has all the settings. I'll open that. And so what's it called now? The map is loaded because we have already launched the localization node. Sorry, the localization launch file, and it has provided the map. And so we know the robot is at this point. So what we're going to do is 2D pose estimate. We know it's facing towards the two cones. It's almost in the middle, not exactly, but I'll just take a guess. Wait 1 second, let me just launch it. So let me just restart the system, I guess.
Actually, I think since it's the top of the hour exactly, the controllers will be restarting from 1 minute for 1 minute. So could you try and move the robot, and we'll confirm this?
Okay.
I don't think it will move.
Yeah, it's not moving.
Okay, so let's give it 1 minute, guys.
Okay,
this is because.
So I'll just continue with the presentation.
Yes, please.
Yeah. Okay. Sorry. So yeah, so the second part was localization as what we were trying to do. So what is meant by localization? It refers to the robot's ability to determine its position and orientation with respect to the environment. and it's typically represented by a map. We use a lot of AMCL, which is adaptive Monte Carlo localization. It is basically a probabilistic method for localizing system for a 2D movement in ROS. We implement the AMCL localization approach using a particle filter to track the robot's pose against a known map, which we created in the last section. So the configuration parameters for AMCL, it is basically categorized in overall filter, laser model, and odometry model parameters, and it's crucial for configuring AMCL for accurate localization. We have global localization, which is achieved by distributing particle across the map and moving the robot to identify its location. And global localization also means that the person and the robot does not know the position, and when you move it across, the particle size decreases. So basically now the robot, the more decrease in particle size is basically higher probability of robot knowing where it is in the map. So yeah. So here we come towards path planning. And so what is meant by path planning? Path planning basically involves finding a trajectory from point A to point B while avoiding any obstacles along the way. So the nodes we launch in path planning is the planner node. It computes the path from point A to point B while avoiding the obstacles. We launch the controller node, which performs reactive path planning to avoid the dynamic obstacles, meaning that if you throw in like a bottle or something and it generates wheel commands. The behavior tree navigator node, it coordinates the path planner and controller nodes, and it also allows flexibility in navigation tasks, and it simplifies robot behavior when, for example, recovery, backup, spin. And the recovery server node, it executes the recovery behaviors if the robot encounters an obstacle or gets stuck. Many of the times it waits for the robot to stop its movement, and then the recovery happens. And the recovery basically uses local cost map, which we'll be looking into in a bit. So I'm hoping to show the demo now.
I think, yeah, you're ready to go. You might have to close the streaming window and open it again.
Okay.
Oh, no, you don't even have to. Great.
Yeah, great. Okay. So yeah, so as I was saying, I guess I'll build it again.
Good practice. Always to
and
make
yeah,
sure.
So source install setup.bash, definitely very important. And then localization. First, I'll just open ROS to show that how the map is being provided. Okay, so now first we open the configuration file. I'll open the path planner because it has everything. And once I do the localization, launch the localization node, it provides the map. Now we know that the robot is right here between the two cones. So we will basically do a 2D pose estimate. It's looking right between the thing. All right. So now, as we were talking about the particle filter, right now it's increased, it's distributed all along. It doesn't, so there's a low probability of it knowing where it is. Now, as we move the robot around, you will notice that I think the stream here on the right-hand side is lagging, but on the left-hand side, when the robot is moving, rotating, you can see that the particle cloud has decreased. And now what we can do is, because it's more used to the map, we can launch the path planning. And so first, I will like to give it a goal using RViz. So let's say I give it a goal here, and it will move towards here, right? Now in the project, we had to save the goal positions and then go to those defined positions. So it has said goal succeeded. So let's now give it, first of all, corner 1, which would be right here near the construct. So let's give it a go.
For the audience, I think the right side camera froze, so just look at the left side camera. Nice. Okay, cool.
And so as we can see, it's waiting for it to get into the correct orientation, I believe. Also, it shows you how many recoveries it did. Actually, it's very fast. So here, number of recoveries is 1, but Yeah, I
So this
think,
is your client that's we are seeing in the terminal output.
yeah. I think like if I give it a push, maybe, yeah. So, okay. All right. So now it has cleared the go. It has reached the orientation in which I saved it.
Okay.
Now let's go to pedestrian. No, okay. The pedestrian spot, which should be right here. All right. Yeah, I saved it in this. All right. Okay. Now the corner two would be right here, which would be
Uh-huh.
right here on the left screen. So let's go to corner two.
And then we can see actually
That was very close.
very close. Yeah, that's probably because it's only seeing the stick, you know, of the obstacle. It's not seeing the base of it.
Oh, right. Yeah, because the laser is a bit up.
Yeah, a little
Right.
bit higher.
Right. So yeah, I initially thought that was
Awesome.
due to the robot radius definition in the cost map, which I'll explain in a bit. So that was
Mm-hmm.
one of the challenges for me.
Yeah,
All right.
for sure.
So
And
um,
this I'm sorry to interrupt, but this the your client kind of finishing up and you know stopping there means
yeah,
that the goal was successful.
yeah,
So if we were to look at the NAV2 terminal output, we would see goal succeeded.
uh,
So
yeah,
in here, you have NAV2 running somewhere. You have the path planner launch
yeah.
in one of those terminals, I think 701. So
Oh, okay. Yeah.
I
Sorry.
think what I'm
Are you
trying
going
to,
to the
yes, this is what I'm trying to
yeah.
see. And I
Oh, okay.
think when it was, you know, trying to twist around the it was trying to find exactly the point, right?
Exactly.
Okay,
And
understood.
exactly. So with the pedestrian, I decreased the decimal points a bit while saving the spot because it has like seven decimal points, which then it tries to accurately determine its
Yeah,
orientation.
okay.
So yeah, let's continue with the presentation. All right. So I've already discussed the nodes. And so the parameters for path planning are the planner parameter. It includes the planner frequency, the plugin selection, and the tolerance. The controller parameters includes the controller frequency, velocity threshold, and goal checkers. Recovery parameters include recovery behaviors such as backup, spin, and wait, as we saw reaching the first one. So how do we send the navigation goal? First of all, we use an action server to send the navigation goal, and we use the topic to publish the navigation goals. All right, so the way my code works is first of all, navigating to the spots. So I create an action client goal. I send the goal to the action server, and the robot then navigates towards a specific pose. It reads the pose coordinates and orientation from the parameters from the already saved, from what's it called, the saved file,
Mm-hmm.
constructs a goal message. Sorry, I'll just get into the YAML in a bit, and then it sends the goal to the action server. It handles the response asynchronously because the robot works on ROS1, and it spins the action client node to keep it active until the goal is achieved. And so how I save the spots is basically I use the topic initial pose. Um, I basically create a callback function called pose position callback, and I subscribe to the topic, providing the initial position of the robot via ROS. It listens for the initial pose, and once it's published, it records it into a dictionary. Now I have in my code basically a list which it iterates through, and so it's able to save. So for example, if I save when I give it the first position, it will save as corner one, second position as corner two. Only the third position I named it as pedestrian, corner four, and then corner five.
Okay.
Okay, and then what's it called? The obstacle avoidance. So this is basically where the cost map comes in. It's a 2D representation of robot sensed obstacles on a grid map. It helps avoid known obstacles on the map. So we have two, global versus local. The global is based on a static map and is used for long-term planning. The one on you see on your left is global. Local is the one you see on your right. it's based on new obstacle and used for short-term planning. And so the configuration parameters here are update frequency, publish frequency, global frame, and the robot base. And the layers are static, inflation, and obstacle, which we had to define in the controller configuration file. So each grid cell contains sensor detected obstacle information. Cell cost can be unknown, free, occupied, or inflated, and colors denote collision likelihood with obstacles. As you can see, when it's closer to them, it's red. And so it's utilized by controller planner and recoveries for safe and efficient task completion. And so the challenges I first came across was I initially encountered a lot of error messages using Gazebo. I do not know why, maybe because I was used to Gazebo and ROS2 basics, but however, running it in the navigation, it would, first of all, when you do source install just to set up, it gives you random message errors sometimes. And one thing I learned was the learning, like use of new libraries. For example, now with the YAML file, YAML ain't markup language, it's basically updated without the need of building the package again. However, if you want to use those values, you have to build the package again. So for example, right now, like if I've saved the spots, however, I built the package with previous spots. While saving the spots, it will updated like live. However, when you want to use the new spots, you have to build it again. This I learned with trial and error. It's because the files are based inside install and log files. So you have to be careful with that. And it supports various data types, which is nice. And it's also readable, which is very good. Making the map initially, so I was kind of going a little bit for perfection. I wanted the cones to be exactly as it is on the real map. However, it was a bit different because the simulation, first of all, the cones don't move. The robot gets crazy.
Yeah, and the real obstacles, they move all the time.
They move all the time, right? And I wanted to do it on the real robot. However, sometimes when I used to connect with the real robot, the obstacles would be all over the place. So I just went with simulation. The object resolution and placement. I believe the placement, for example, on RWiz, we could have more objects. And because I learned that when you give it a map file, later on in the units, they teach you that you can edit the map using GIMP. And so I was planning for my future, for trial and error. Now that I can navigate, I was planning to paint a track on the map, and then I would then give it to the robot, and then I would make the robot follow the map and follow the tracks, so it stays in the lane. So it thinks of the lanes as like an object, so it doesn't collide with them. And so if there are more spots on RWiz, it would be easier to localize as well. And so one more problem I came across was the global status error, which is, I don't know, it gave me errors in RWiz with the fixed frame. I initially thought that had to do with the TF frames, but when I've used to view frames, all my frames were connected. For example, the base link and the ODOM frame would always be connected. However, I did not know, so I went to the community. I looked up online, and it was basically, even if I basically focused on the small pictures you provide in your units, I noticed that error would sometimes show up there as well. So I had to just overlook it.
So this error is very interesting. Very, very sorry to interrupt, but very. I think this is RWiz. This is the inability of RWiz to handle TF messages because they're a little bit special and they have to come in at a certain frequency. And if you miss one of them, if RWiz, for whatever reason, because it's in Barcelona and you're over in Houston, something drops, then the RWiz catches that, and it's like, there's an error, I can't find that TF. So it's definitely RWiz's inability, I think, in this case of basically not being robust enough and kind of like yelling at you when these things happen. But that's I think that's the reason.
And overall, it was a great learning experience. I got to learn about Digistra's algorithm, which helps you calculate the shortest path, the A-star algorithm, which calculates the fastest path, and we have use A-star equal false or true. that parameter in the configuration file. And yeah, it was overall a good learning experience. And I'm looking forward to doing the drone course now. However, it's in ROS 1. So sometimes I would open up navigation and write cat can make because I'm so used to ROS 1, like,
Yeah.
because I keep shifting. But yeah, looking forward to it.
Yes.
These are the references, and thank you for listening to my presentation.
Awesome. Awesome. Thank you very much, Mohammed. So let me here give you a nice little applause. Thank you. Thank you. Very nice presentation. Do you mind stopping sharing your screen so we can kind of see face to face? Awesome. Great. So great. Congratulations, Mohammed. Really, really nice presentation. Really clarifying and complete presentation. You answered a lot of the questions I was writing down for you. So I just want to congratulate you. And we saw the demo was very efficient, and we saw that you built the nav2 and the application of saving your spots to then send them to the different places. So congratulations, Mohammed. Let me ask you a couple of questions.
Sure.
So the first one is the sort of, what do you think this environment requires you to do in order to fine tune this navigation too? Because we saw, for example, the robot kind of at the end have some trouble finding the goal. Why do you think that is, and what would you change in the environment to fix this if you were able to come here and change it around?
Okay, so I mean, first of all, I would definitely put more objects in the thing so it can localize better. And when you're building it, I would make sure I go across all of them so the resolution of the map is better. Secondly, when you're saving the spots, as I mentioned, that I would decrease the accuracy of the spots because then it's hard for the robot to actually get fix itself on that position, because towards like 7 decimal places, I think it's a bit too much when you're on a bigger scale, right? And maybe.
What do you mean by save the resolution of the spots? What does
So
that?
for example, like if I show you the spot file, it would have 0.xxxxxxxx, which
I
is
see.
2.7 decimal. So I think that's way too accurate. And when you have a bigger map, you don't need that much accuracy for, like, for example, let's say corner 1. So yeah, I would change those.
Yes, you also, yes, perfect. That's why I wanted to talk about, because yeah, there's two things. I'll start with the second because you just mentioned it about the decimal points of your. Yes, that is something that obviously will make the robot be like, I'm not there yet, So keep trying. But there's also a parameter in nav2, like XY tolerance in the controller.
Okay. Yeah.
And you can increase that in either the orientation, because we saw, like, I think it was there, and it was kind of like that meant that the recovery server kicked in, so that's good that it was trying to fix itself. But yeah, so on that side, there's that tolerance that you can adjust, right? And then there's the difficulty of the map that you talked about, that adding more obstacles will help it localize better. And it's also a very symmetrical map, right? So I don't know if you experience that. Sometimes you're moving around the map and you're looking at the particle clouds.
Yeah.
And suddenly it kind of like switches back to the opposite end because it's too
symmetrical. Okay.
Too symmetrical. So those two things are important, and in order to sort of fine tune these applications, and enough to, if you're using a map, you're gonna have these issues with every single robot, right? So you have to sort of look at your environment and look at your robot in order to see, what you want in case for precision, or do you just want to go around and then another node would kick in and do precise movement. That's, for example, how charging works. You have an extra little tag in there that says charger, and the tolerances are bad because you don't want to get to the charger with navigation. You send it close enough, and then you kick in another node to do that precise movement. Okay. And the other question I have is just basically, so the we saw you give it an initial position in the beginning to sort of localize the robot. So do you know of any ways to avoid? What if you couldn't give that initial position to your robot? What would you do about this?
Well, the only thing I found while reading was via global localization.
Exactly.
Um,
Yes.
so yeah, because when the person and the robot, they both don't know where the robot is. So yeah, you use
Yes.
global localization.
So in that case, there's a service that NAV2 provides, which is nice. I think it's AMCL actually that provides
Mhm.
it. That is the global localization. So what that does, it spreads out the particles all over your map, the AMCL particles. But then that's not good enough because that means you're telling the AMCL, I don't know where the robot is.
Probability is huge.
You
Yeah.
know. So one quick thing is to create a node. Basically, what I do for my robots in this scenario is I just move it around a little bit. You know, I make a quick node that is subscribing to the laser and publishing on command vel in order to not crash. So I just tell it, move around a little bit, and that way the particles start converging. So that is besides, I think this is the one thing that is the most useful once you try to sort of automatize, like make this automatic, is to call that service, make the robot move around a little bit, and go for it. I trust too much localization. I don't even localize it sometimes before I send the goal, and I just trust that NAV2 will do its job and find itself.
And sometimes while I'm defining the goal via ROS, I would accidentally press the localization, and then it would just completely mess up everything,
Yes.
and I have to restart it.
Yeah.
So
So,
yeah, definitely I'll look into global
all right.
localization.
But yeah, other than that, Mohammed, a really, really nice presentation. So again, congratulations, and yeah, hope to see you around for the. We don't have a drone real robot lab yet to see a project there, but hope to see you around and congratulations.
Thank you so much. Thank you so much.
All
Have a
right.
great day.
You too. But just to close out everyone, for everyone that is watching, this is what you can do when you take our courses, that offer a certificate. You need to come and show us what you've learned with a presentation. And so I invite everyone to do this to get that experience of implementing your programs on a real robot, like Mohammed did. And that's it for us, guys. So thank you again, Mohammed, and we'll see you guys next time. All right. Bye-bye.
Bye.